Here we're going to get into the beginning parts of postulates and proofs. So we're going to start off with our postulates. Now I like to think of postulates as they're kind of like the undefined terms of geometry. We need them to build on. So these are things that you just accept to be true. There's no way to prove that they're true. We just accept that they're true. And then once we have them, we can use them to prove other things. So this first one, it says through any 2 points there is exactly one line. And what I like to think about this one is just take a piece of paper, anything, draw 2 points on it. Can you make one line go through it? The answer would be yes. Now could you make a second line go through those 2 points? No, you can't. It's going to be the exact same line. You could put those 2 points in space and you could make one line go through them. And that's what that postulate is saying. Now the next one, similar in the fact that we're dealing with points again. Now we just have 3. But if you have 3 points that notice are not on the same line, then there's going to be exactly one plane. Basically what that says is if you put 3 points anywhere, you can make basically a sheet of paper, extend it possibly, and that sheet of paper will touch all 3 of them. Now the other one, this next one kind of goes back to what this one says, go in the other direction. Now it says if you have a line, then it's going to contain at least 2 points. Now in all actuality there's many points on it, but there's going to be at least 2 points on any line. And then this one kind of goes the other way from the second one that we had. If you have a plane, there's going to be at least 3 points. And again, there's going to be many points on that plane, but there will be at least 3 of them that are, notice, non-collinear. If I go down, this one is sometimes referred to as the flat plane postulate, because when you read it, it says if 2 points lie in a plane, then the entire line containing those points lies in that plane. And then what I like to think of here is take a sheet of paper that would represent your plane, put 2 points on it, don't care where you put them, and then make a line go through those 2 points. Well, is there any way that that line will ever get off of the piece of paper? And again, realize the paper is going to extend, and so will the line. But that line is never going to jump off of the paper anywhere, and that's why I like to think of it as the flat plane postulate, because lines are straight, which means that plane's going to have to continue to extend out, and it's always going to have to stay flat. You're never going to get a hill in the plane. This one goes back to if you take 2 lines and make them intersect, they're going to intersect at 1 point and 1 point only. There's no way to get those lines to curve so they'd come back and touch twice. So lines will intersect at exactly 1 point. And then the next one deals with planes intersecting, and they're going to intersect in a line. And I like to think of this, so look at 2 walls. Those would represent planes. If you look at where they come together in the corner, the geometric figure that's actually there is a line. So this postulate makes sense that 2 planes will intersect in a line. Now our first theorem is referred to as the midpoint theorem, and notice I've abbreviated the word point, and sometimes I even leave out the word I, MD, PT for midpoint. Now the midpoint theorem says exactly what you see there. If M is the midpoint of segment AB, then segment AM is congruent to segment MB. And I like to draw a picture of that. So what the midpoint theorem says, if M right here is really the midpoint, then the segment, I'm looking at this to the left, which is segment AM, and the segment to the right of the midpoint, segment MB, those 2 things are going to be congruent. That's all the midpoint theorem says. Now we're going to get into writing proofs more and more. This is just going to be the beginning stages of it. But I've liked what the book that we use right now has done. It says there's 5 parts to a good proof. The first one is to state what is to be proved. Now that's going to be the theorem or the conjecture. It may ask you to prove the midpoint theorem. So then what you want to do is actually write down what is the midpoint theorem. Instead of just writing down midpoint theorem, you'd write down if M is the midpoint, then segment AB or segment AM is congruent to segment MB, like we saw on the last slide. That would be part 1. Number 2 would be list all the given information. Now, if you have done step 1, this won't be too bad because your given information you're going to find in the hypothesis of your if-then statement. Next, this is the one that I love. draw a picture and add on this. Not just draw a picture, but mark it up. I didn't put that in here. I should fix this slide to put and mark it up right there. Step 4, state what is to be proved, and some of you are going, but Mr. Rue, you already said that in number 1. Now here's the difference between number 1 and number 4. Number 1 was that theorem or conjecture. A lot of times I would suggest trying to write that in if-then format. Step 4, it's just saying rewrite what the conclusion is. That's what you're actually trying to prove. So this is the whole conditional statement, and this is just the conclusion of it. And then finally, we're going to write the proof. And we're going to go through proofs, and at first it may be a bit of a struggle, but hopefully as time goes on you'll get better and better at it. So here we go. We're going to take that midpoint theorem that we talked about earlier, and we're going to write a proof for it. We're going to prove that it's actually true. And I'm going to go through my 5 steps. I have them all right here. Step 1, step 2, step 3, step 4, and then down here step 5. So we have to state what is to be proved. And again, this one in step 1 is state what the actual theorem says. So all I've done is I've taken that sentence from a few slides ago, literally copied and pasted it right here. So you just write it down. Step 2 then is list the given information. Well, again, you're going to find that in the hypothesis of this first statement. So I'm going to say given, this is what I know has to be true. I know that M is the midpoint of the segment. And again, being this is, basically these are variables, this could be any point and this could be any segment. So it doesn't have to be M in segment AB, but for the sake of this, of what I wrote up here, I'm going to use that. Next I'm going to draw a picture. Well, what do you draw a picture of? Exactly what it's talking about. We have a segment, and then we have M at the midpoint. And I'm going to draw it like this. Here's my segment AB. I put my point M on there. Next, I'm going to state what we're trying to prove. We're trying to prove, remember, what's in the conclusion, that segment AM is congruent to segment MB. So again, took this piece right here and just rewrote it, because that's what I'm trying to get to. Now this first proof that we're doing, notice it said it's a paragraph proof, so I'm just going to write a paragraph. I'm going to write English sentences to prove that this point right here is actually the midpoint. So my first sentence comes to this. If you look in your book about the definition of a midpoint, well, the definition actually tells you that the length from one endpoint to the midpoint is equal to the length from the midpoint to the other endpoint. In other words, the measure or the length of segment AM is equal to the measure of segment BM. And I know that's very similar to what this says, but it's not exactly what it says. So I'm using my definition to start my proof and say this. Now that I know that these two lengths are equal, well, if the segment lengths are equal, then I know that my segments are going to have to be congruent. So again, by the definition of congruence, I will know that segment AM is congruent to segment MB. And again, your definition of congruence, my basic definition, same shape, same size. Well, here we know we're talking about a segment. Here we're talking about a segment, so same shape, same size. This is telling me that those two segments are equal in size. Therefore, I use that definition of congruence to state this. Now notice, I have stated in my proof what I was trying to prove. Once you get to that point, you're done. I'll ask you to prove something. You've proven it. Quit. You don't have to go any farther. Now here we have some questions, basically, or statements that we want to know. Are they sometimes true? Are they always true? Or are they never true? In my first one, if plane T contains line EF and line EF contains point G, then plane T contains point G. Looks like a lot to start, so what I've done is I've just broken it down and I drew a picture. I have the whole picture here, but I'm going to explain how I did it. I started and I drew plane T. Drew my little parallelogram here, put the T in the corner so I know I have plane T. Then it says that plane is containing line EF. Well, then I put in my line EF. And then it goes on, it says line EF contains point G, so then I put point G on top of my line. Well, this if-then statement says if all of this happens, then plane T contains G. In other words, G has to be on the plane. Well, I look at this and is G on the plane? Yes, it is. The question I have is there another way that I could draw this so that I could get point G to not be on the plane and still be on line EF? And the answer would be no, it's not going to happen. This is really the only way we can draw it. And yes, I could change the direction the line's going and where the points are at, but it doesn't matter because point G is still going to be on plane T. So my answer for this one is going to be always. In my next example, this one I have line XY, and this tells me that point X is lying in plane Q and point Y is lying in plane R. And then this goes on to say then, if that happens, plane Q has to intersect plane R. Well, I have a couple examples here. So my first one is, let's try to look in this classroom and see if we can find this, make this situation. So I'm going to say plane Q is the north wall, plane R is the west wall. Now what I'm going to have to do is I'm going to have to put X on the north wall, and I have to put Y on the west wall. Well, can I make a line go through those 2 points? Definitely. So I've taken care of this first part. It goes on and it says then plane Q intersects plane R. Well, is the north wall intersecting the west wall? You look over there and you go, yeah, it is. So right now I know that this is going to happen at least in one situation. Now if I can get this to happen in a different situation where maybe these planes don't intersect, then I'm not going to be able to go with always as the answer. I'll have to go with sometimes. But right now I know it's at least sometimes and possibly always. But then I think about another situation. Well, what happens if plane Q is the ceiling this time and plane R is the floor? Well, can I put X on the ceiling, point X, and can I put point Y on the floor and make a line go through the two? I can do that. So then I've satisfied again the first part of my statement. But now it says then plane Q intersects plane R. Well, is my ceiling ever going to intersect the floor? No, because those planes are parallel. So here I have an example of where they actually do intersect, that the statement says, and here I have an example where they do not intersect, which is contradictory to what the statement is saying. So for this case, I can't go with always, but I'm going to have to go with sometimes. And then here, my last one, I have line GH contains 3 non-collinear points. We'll go back to your definition of non-collinear. Points not on the same line. So is it possible to take 3 points that are not on the same line and put them on one line? Well, the answer is no, I can't ever do that. Not possible, so this is a situation where this will never ever happen. And that's going to conclude the start to paragraphs and proofs.